So welcome back everyone, and as you have seen in the thumbnail, we will study a very interesting concept today. You all have heard about Snell's law in optics, and we use it very frequently, right? That mu into sin I equals to constant, or in some other forms as well. Sin I by sin R is refractive index ratio of two mediums. So it's very common, but now today we'll use this Snell's law in kinematics in some specific problem solving, right? So you must be wondering how is it possible, but we'll explore this through this video. The Snell's law is very helpful in kinematics problems as well, and it is basically based on Fermat's principle. So we will do some problems as well. I'll cover one IRODOV problem in this video and also one pathfinder problem in this video, or maybe in some another video based on the same concept. So let's start. Fermat. So first let me brief you the Fermat's principle. What Fermat's principle state? It states that light always takes the path in which it will be traveling in shorter time, right? Means whenever there is some interface between two mediums, then light will bend and it can follow any path. So which path it will take, that will be decided by the path which will take least time to reach, right? So that is what Fermat principle state. And sometime in kinematics we will find that questions are asking about finding least time to reach from one point to another, and both the points are in some different mediums, and the particle which is moving has different velocities in both the mediums. So that's a very tricky case to handle, I guess. I mean, yeah, calculus is there, you can do this with the calculus, and I'll tell you the conventional method as well, taking some arbitrary root as a function of one parameter and differentiating that. But I'm more interested in solving those kind of problems using Snell's law. That's why I'm making this video. So first take a general case here, right? Let's say here is medium 1 and this line is separating both the mediums, and below this line there is medium 2, and a particle starts moving from A and he has to reach B in the medium 2. In medium 1 velocity of the particle is u, and in medium 2 velocity of the particle is v. So it can take any arbitrary path. It can move like this and go like this, it can move like this and go like this, and this and this. So among every possible paths, we are interested to find the path which will take the least time to reach from A to B. So let us find out which one is this. I'm assuming that, wait 1 minute, yeah, this one is the required path that we are interested in finding, and this path will ensure that the particle is reaching from A to B in minimum possible time. And this is the perpendicular to the interface, and as A and B points are fixed, so distance between them is also fixed. Let's say this distance between them is L, this distance is x, so by default this distance will be L minus x, and these two are the perpendicular lines I have drawn on the interface from points A and B respectively. Let me name this point as C, this one as D, this one D, and this one as E. Okay, and I'm marking this angle as I, this angle as R. Then so time to reach A to B, I can divide it into two parts: time to reach C from A plus time to reach B from C. As both the mediums are different and speeds are different, so I'm breaking the whole journey in two possible parts. And for time taken to reach C from A, you can write it AC upon velocity in medium 1, that is u, plus similarly you can write BC upon V. Okay, so and this one, let's say the perpendicular distance of the interface from A is d1 and BE is d2. So by Pythagoras theorem we can write AC as d1 square plus x square upon u. Sorry, AC is root over d1 square plus x square, and this whole term will convert into this one upon u, right? And next term will be root under d2 square upon L minus x square upon v. And I am trying to minimize this function, right, DAB. And as you can notice that variable is only x, u and v are constant, d1 and d2 are also constant, as a and b are two given points. So let's differentiate as we do for maxima and minima problems with respect to x. So we can write this as 1 by 2 into root over d1 square plus x square into 2x plus 1 by v into 1 by 2 into d2 square plus L minus x square minus of 2 into L minus x. I'll equate this to 0 for minimum possible case, right? So let's simplify this one. This 2 gets cancelled, and we'll get here 1 by u into x upon root over d1 square, d1 square plus x square plus 1 by v into, let's put a minus sign here only, L by x into root over d2 square upon L minus x square. Or otherwise take this whole term to the right side and equate this. Okay, and now come back to the figure. What is root over d1 upon, 1 minute, what was the term, sorry, x upon root over d1 square plus x square it was. Okay, so yeah, so let me change a bit the diagram. I mean, let's not assume this angle as I, it's better if I assume this angle as I. As you can understand, I am denoting I and R just to keep the analogy with Snell's law. And finally we can show that mu sin I equals to mu1 sin I equals to mu2 sin R, kind of that expression I am trying to manipulate from this differentiation. Okay, so this one is d1 square upon x square from Pythagoras theorem, and you can write this one means BC as d2 square plus L minus x whole square. So x upon, from triangle ADC, it's a right angle triangle, you can conclude that x upon root over d1 square plus x square is nothing but sin I, as this angle is also I by alternate angle. And from triangle BCE you can clearly observe that L minus x upon, oh my bad, this one also need to be changed. Let me take this angle as R, so this angle will be also R as an alternate angle. So L minus x upon root over d2 square plus L minus x square will be nothing but sin R. So now you can clearly understand that this term is sin I upon u and this term is sin R upon v. So this is nothing but the Snell's law statement, I mean the mathematical form of Snell's law, isn't it? What we write in Snell's law? We write that it is we write it as mu1 sin I equals to mu2 sin R, where mu1 is the refractive index of medium 1 and mu2 is the refractive index of medium 2. And as we all know that mu equals to nothing but c upon v. C is constant as it is the speed of light in vacuum, and v is the respective speed of light in that medium. So mu1 sin I, it is also proportional to 1 by u times sin I, as mu is inversely proportional to the speed of light in that medium. and mu to sin r you can write as 1 by v times sin r. So this is also an alternate form of Snell's law only. So what's the conclusion? Is the conclusion that whenever in some kinematics problem we are asked to find about the least possible time to reach from a particular point to another point in different mediums, then we can assume an arbitrary path and then differentiate that. But just for our convenience, what we can do is that we will assume that a light is traveling, and whatever the path light would have followed, we will follow that path for minimum possible time. We are just vanishing some intermediate steps, this much only. Otherwise you can solve as conventional method. I mean, this one is as a proof you can take, or otherwise you can start from step 1, I mean assuming x and all those steps. So let's use this in some problem. Okay, let me take a problem from it as the IRODOV problem. We'll apply the concept that we have just learned on this problem. So let me read out the problem once. From point A located on a highway, one has to get by car as soon as possible to point B located in the field at a distance L from the highway. It is known that the car moves in the field eta times slower than on the highway. At what distance from the point D one must turn off the highway? So from A to C, then C to B, and we are interested in finding the path in which it will take the least time to reach B from A. And let's draw this perpendicular to the interface, and we are trying to apply Snell's law, okay, as if there is a light ray and is having refraction in both the mediums. So this angle is 90 degree, and this is the normal, and this is the, let's say, refracted ray. No light ray is going here, just we are taking the analogy. So I'm marking this as angle R, as if angle of refraction. So this angle is also R by alternate angle. So applying Snell's law, what we are writing, that sine of angle of incidence or angle of refraction upon speed of light in that medium is constant. So sine 90 degree upon V, as it is mentioned, the speed on highway is V, but on field it is eta times slower, that is V by eta. So this will be sine R upon V by eta. So V gets cancelled, sine 90 degree is 1, so sine R will be 1 upon eta. And from geometry of triangle BDC, yep, and from triangle BDC using trigonometry, you can write DC upon L as tan of R. So the DC will be L tan of R, right? And tan of R will be, as sine of R is 1 upon eta, tan of R will be 1 upon eta square minus 1. So it will be L into 1 upon eta square minus 1, and we are asked to find DC. So this is our answer for this question. And if you don't know this method, what could have you done? You could have taken an arbitrary path, just like the previous problem. Let's say AC length is X, and then DC length will be, as AD is fixed, you can assume some L0, and DC will be L0 minus X. And all the steps what we have done in generalized case is you can do here as well. So again I'm repeating that I'm just vanish some intermediate steps, and if you know this result, this is nothing a new result. You knowingly or unknowingly use this result for this kind of problems. But if you know that for what condition it will be minima for time, that this relation of sine and velocity, then you can quickly solve this kind of problems. So that's all for this video, and I will also take up another problem from Pathfinder on similar concept, a bit more lengthy on calculative side, but not that much conceptually difficulty. I think after this you can also try that one. but I will take up this problem in next video.